Equilibrium is also known as statics, and it is a pretty simple concept. It is just the physics of things that aren't moving. We call them in equilibrium. So for instance, in this picture, we've got a nice suspension bridge and a lot of nice buildings. This is the San Francisco skyline and the Bay Bridge. And we want all of these objects to be in equilibrium. It's not good to have a bridge that moves around a whole lot or buildings that move around a whole lot. This is in fact the older Bay Bridge. They've built a new one in the last couple of years, but I couldn't find a nice picture of that bridge with the skyline and everything like this one. So in order to be in equilibrium, we already know that the forces have to be balanced. Whenever an object is at rest, we know that the net force, if we're talking about the vector notation of net force, then that's equal to 0. We can break that up into components in each direction. We've solved lots of problems like this. For instance, a chandelier hanging, we could set this component Fax equal to Fb, and we could set Fay equal to gravity, and we could solve for unknown things just using the fact that the net force is equal to 0. I'm not even going to bother working through this. But is that sufficient? I once listened to I don't know if he was an architect or an engineer who helped build a basketball arena, and he mentioned how he just used one equation, net force equals 0, so that the building didn't fall down. But he wasn't quite right. For instance, in this situation here, if I assume these two forces are equal, they're acting in opposite directions. So when we're writing our net force equation, that doesn't take into account where on the object the force is acting. So the net force here is indeed 0, but is this in equilibrium? No, it's going to start rotating around this way. So in addition to our requirement of the net force being 0, you guessed it, we also need the net torque to equal 0. Now we don't have x, y, and z components of torque, we just apply this once. But the nice thing about torque is we can choose any location on our object that we want, and if it's in equilibrium, those torques will sum to 0. It doesn't matter if it is where the object would tend to rotate or not. We can choose any location, and I'll show you some examples where that's useful. Here is our first example. If we have something maybe like a diving board, or just imagine a board with a couple of blocks underneath it or something like that. This, by the way, where you have an unsupported span that doesn't fall because of the forces back here, is known as a cantilever. Some famous examples are this house designed by Frank Lloyd Wright. It is known as falling water, and there's lots of cantilevered segments in this house here. You can also build cantilever bridges where the support is here and then it spans out over an unsupported section. You can only go so far, so you couldn't have a huge unsupported section, but as long as it's small enough, you can. Alright, let's look at analyzing this situation here a little bit. And if we know the mass of this board or whatever here, 5,000 kilograms we'll say, then we can find the weight that each of these supports is lifting up. So we can start out with our sum of the forces. There are no forces in the x direction, so we just have one force equation, which is the two up forces equal the down force. Nice and simple. And then we've got our net torque equation. Now, as I just mentioned, we can sum these torques about any point we want. So we could do it about this end, in which case we'd have a torque from all three of the forces acting on it. But why make life more difficult when we can do the torques about a location of one of these forces, and then that lever arm for that torque, or for that force, is 0, so there is no torque from A about that point. And it just makes our calculations a little simpler. So from this frame of reference, so we'll say the torque about point A, we have a torque due to force B, and that's the force, the lever arm is 20. And then we've got another torque due to gravity acting on the middle of this beam here, and we have to think about whether those are causing it to rotate in the same direction or not relative to this pivot point. So if we were rotating about that pivot point, this would cause the beam to rotate that way, the force from B, or the torque from it. The torque from gravity would tend to make it rotate the other way, so we are going to subtract gravitational force. The lever arm for this, gravity acts at the midpoint of the beam, which is 50 meters long, so the midpoint is going to be 25, and the torques have to sum to 0. So we can jump right in and solve for the weight supported, or force B. It's going to be 25 over 20 times gravity. 25 over 20 times the mass. I'm going to run out of space here. Maybe not. 9.8. Cram it in there. And we get the force is 61,250 newtons. So quite a bit of force. And then if we plug this back into this equation here, we're going to get the force supported by A is gravity minus the force supported by B. Gravity is 5,000 times 9.8 minus 61,250. And you might have noticed this number is going to come out to be smaller than that number. This is 49,000 minus 61,250. And that gives us a force of negative 12,250. Is that a problem? If we get a negative sign, did we mess up? Is this number wrong? No, it's not a problem. All that means is that our initial guess for which way that force was going was incorrect. Instead of going up, that force is going down. Which you might have realized when I mentioned that this thing would tip over if it weren't supported on the back. You don't make it not tip over by pushing up on the back. You have to pull down on the back. But another point is sometimes you'll have some pretty complex situations and you're not sure which direction the forces or torques are acting. So just go ahead and pick a direction. It doesn't matter as long as you're consistent with your sign conventions. Then things might come out with negative signs, and that just tells you that you chose wrong, but no big deal. By the way, if there were no force here, this thing would tip over because this would be the pivot point, if this support here didn't exist. And the center of gravity is not over the pivot point, so we're going to look at that briefly. For things to balance, the center of gravity has to be over the supporting forces, or in such a way that it will cause them to move so that they will then be over it. So if you tip a fridge over a little bit, the pivot point is here. Center of gravity will tend to cause it to rotate that way, and it will go back down. Whereas if that center of gravity gets past this pivot point here, then this fridge is going to tip over. When it's on the ground, it will be balanced again. But also, we had a test question where we looked at this similar idea. If you hold a weight, you tend to lean in the opposite direction, which might be kind of counterintuitive. You might think, oh, that weight should weigh me down and make me lean in the direction of the weight. But if you've ever carried a bag or something, you know that if you have a heavy weight on your back, you lean forward. If you're carrying a heavy bucket or something, you lean in the opposite direction so that you can keep the total center of mass over your feet, because if it's not, you will fall over. There's also a distinction between a situation like this pendulum here versus this pencil. They can both be in equilibrium, so you could get a pencil to stand up nice and straight here. That would be equilibrium. But if you deviate from that equilibrium a tiny bit, you are going to fall away from equilibrium rather than return to it. So this is called an unstable equilibrium. And this one over here is called a stable equilibrium, because if you disturb it from equilibrium, the forces tend to push it back in the direction of equilibrium. Unstable equilibriums are sometimes called metastable states as well. So there is that. Let's look at one more example. I would pay close attention to this one because there's a lot of good tricks for doing these types of problems that you'll see in this example. So without further ado, we've got this ladder here. It is 5 meters long, 4 meters up a wall, some unknown distance away. Actually, if we know that's 4 and that's 5, it's pretty easy to figure out that this length here is going to be 3 from Pythagorean theorem. And we've got the wall exerting an outward normal force here. We've got the ground exerting an upward normal force here. And we've got some friction. This is due to friction here. The wall doesn't have any friction component to it. We have a smooth frictionless wall and a rough surface on the bottom with friction. And we want to solve for these two forces here. Those are our unknowns. We know the mass of this guy, and that's about it. So let's jump right in. We can do an equation for the horizontal forces. We know that the force to the left has to equal the force to the right. So the force of the wall equals the x component of, C is for concrete. We're assuming this ladder is on concrete. So there's one equation. Then vertically, we've got the up forces equal to the down forces. We are assuming that this is in equilibrium, nothing's moving. So in that case, we've got the vertical component of our concrete force, the normal force from the ground, is equal to mg. And we know mg already, so 12 times 9.8, and that works out to be 117.6. So it looks like we're almost there, right? Well, we got a bit more work to do. One thing to not do is to say, well, if I know this is 5, 4, and 3, I can find this angle here, and I can just write this as cosine of FC, write it as FC cosine theta. And this guy is FC sine theta. Well, the problem with doing that is that this FC, the total force, doesn't act directly up the ladder. So we can't find theta. Theta of the force doesn't equal theta of the ladder. So this is true, but it's actually not going to be useful. So don't go that route. All right, so let's look at our torque equation and see what that gives us. We've got a couple of forces acting here, so that's going to be a good choice for our pivot point, or our axis of rotation. So we want the sum of the torques, I'll just call it about C, about the point on the concrete. And here is a situation where using the perpendicular distance rather than the perpendicular component of the force is going to be quite a bit nicer, and I'll show you why. So here we've got gravity acting on the middle of the ladder, so I'm going to do mg times the lever arm. Well, as I mentioned, you could find the perpendicular component of gravity, but the lever arm, if we extend out this force here and just take the perpendicular distance, if I know that distance is 3, the perpendicular distance is just 1.5, and that's going to be easier than trying to figure out with trig what angles are complementary and all of that jazz. Okay, over here I've got another force, and that's going to exert a torque. This gravity is going to try to make the ladder rotate this way. The normal force from the wall is going to make it rotate that way, so we need to subtract these. So the force from the wall. Now be careful that you don't use a distance of 4 meters. What you have to do is extend out that force and then take the perpendicular distance from the force, okay? So the force is not pointing that way, so you can't take, oh sorry, I said don't use the 4. I meant don't use the 3. Since you used 1.5 for gravity, don't use 3 for the normal force from the wall. Do use 4, so strike that thing when I said don't use 4. Alright, so that is our perpendicular distance, and again that works out a little simpler than finding the perpendicular component of the force. Feel free to do that if you like. But alright, so from this point, again, we can solve for the force of the wall. It's going to be 1.5 over 4 times gravity, which we already found, which was 117.6. And so that works out to be 44.1 newtons, and that was one of the two things we were trying to find. We wanted to find that guy and this guy. And we have one component, right, of this force here. And this guy is equal to the other component. So now, if we just think about this triangle here, I've got 44.4, and I'm going to draw my vertical vector here, since we're adding them to get our total vector there. A little too wavy, but anyway, 117.6. So then we can just use Pythagorean identity here, and we're going to take root 117.6 squared plus 44.1 squared, and that works out to be 125.6 newtons for the force of the concrete. And there you have it. We'll see you next time.